studied vector quantity. The one of okay, 1 second. Just for recap, we have studied two different quantities which describes about the properties of a field, okay, surrounding a charged particle, which are electric force, and electric field. All right.
Yes, sir.
Electric force and electric field.
Yes.
These two quantities are basically vector quantities, right?
Yes, sir.
But now in this chapter we are going to introduce two new quantities, in which the first one is your electric potential,
V.
and V denoted by capital V, and the second one is electric potential energy, right?
U. Yeah. Remember.
Potential energy, you can say it U. These
Yes,
two
sir.
quantities are scalar quantities,
Yes, sir.
right?
Okay. Yes, sir.
Quantities are scalar quantities. This is our topic of this chapter. Okay, in this whole topic we will discuss about it, right? So before starting this chapter, we want to recap some basic formulas related to the work done, okay, which we have studied in our last classes, previous classes of class 11, which are, please note it down, just one
Yes, sir.
second. Electric potential, and capacitance. Electric potential and capacitance, right? This
Yes,
is our
sir.
topic. Before starting this topic, we are going to recap some basic formulas, which are, the first one is your work done by constant force. Work done by constant force, which are W is equal to F dot
F.
S,
S. Cap.
or sometimes it can also be written as F S
F.
cos theta.
Cos theta.
Yeah, F and S are in terms of magnitude, right? Okay.
Sir. Okay.
Yeah, tell me.
Nothing. Nothing.
All right. F is your force. S is the displacement. Okay.
Yes, sir.
This is the displacement due to this applied force. You can say this is your applied force upon the body. And what is your theta? Theta is
Angle.
the
Angle between them.
angle between F and S. Are you clear or not?
Yes, sir.
Okay. Similarly, we have already know work done by variable force. Okay. The equation for the variable force is W is equal to integration of R1 to the R2 F dot
F.
T.
Theta.
Okay. This
Yes,
is your
sir.
equation of work done for variable force. Are you clear?
Yes, sir.
Okay, good. This is your basic formulas which are mostly used in whole of this topic, right? Now, let's start from the first heading, work done in external electric field. Work done in external electric field. Remember here, we are discussing in external electric field, right? Not internal. Try to understand here what is the means of external electric field. Suppose that we have a charged particle of capital Q, right? We know that if it is a charged particle of Q, then it creates a field surrounding itself. We have already know. Are you clear or not?
Yes.
And this field is generated by this charge. Are you clear or not?
Yes, sir.
This field is generated by this charge. Okay. So this is the field of discharge. Are you clear or not? But
Yes,
in
sir.
this heading, we are going to discuss the work done by the charge in external electric field. External in the sense an electric field which is not created by this charge. Are
The
you clear?
charge.
Okay.
Yes, sir.
It is from outside, right? So
Outside.
note it down. Just 1 second. Yeah. We are taking here an electric field like this. This is your electric field lines. Okay. We have
Yes, sir.
taken here a charged particle at this position. We have a charged particle at this position. Now, can you tell me what will happen if we put a charged particle at this position in this field? Remember that this is your field. This is your field. Which type of field? This is your external field. Are you clear or not? Okay. This charge is taken as infinitesimally small in size. Okay. Are you clear or not? Then can you tell me what will happen if you put a charged particle inside this electric field? What will happen? Then we can say a force must be applied upon this charged particle. Am I
Sir,
right?
you're lagging.
Sorry?
You're lagging, sir.
My voice is lagging or screen?
Sir, the voice.
Everything is clear from my side.
Sir, wait, let me check. 1 minute from my side. So 1 minute. Yes, sir. Like I have internet issues, sir, and
Okay.
it's unstable.
It's stable or not?
It's stable now, but in between it just goes down. So
Okay, don't worry. Now, I am just asking to you that what will happen if you put a charged particle at this position A in this external electric field? Then we can say that a force must be applied upon this charged particle in the direction of electric
the
field.
electric field is.
Are you clear or not?
Yes, sir.
Why? What is the reason to? What is the reason behind it?
Sir,
Why it
because
is
it moves
acting
on
along the direction of the
along the
field?
direction of
It
electric
is your
field.
positive charge. Are you
Yes,
clear or
sir.
not?
Yes, sir.
You can write here F of electric is equal to Q into E. Are you clear or not?
Yes,
Okay.
sir.
We are going to write here electric field. Sorry. Electric force, not field. Electric force on charge Q. This is your F of electric is equal to Q into E. Okay. This is your equation number 1.
Yes, sir.
Okay. And now, what will happen
Yes,
if
sir.
you apply an external force upon this charged particle? We are going to apply an external force upon this charged particle in opposite to the direction of F electric. Okay. This is your
Yes,
F
sir.
external. Then we can write here external force
Is equal in Q.
External force to be applied on Q. This is your F of external is equal to, which is equal to the F of electric. And
Yes,
F external is opposite to the F electric. So we can take here a negative sign. Are you clear or not? This negative sign represents that F electric and F external both are opposite in direction. Are you clear?
Yes, sir. So charge won't move, right?
1 second. Now,
Yeah, okay,
we are going to place the value of F electric in equation 2 from equation 1. So you should write here, put 1 into. When you put 1 into, then you get F external is equal to minus of Q into E. Are you clear?
Yes, sir.
This is your equation number 3. Okay?
Okay.
And now we have already know that when we apply an external force upon this charged particle, this charge will displace from this position to this position. Suppose that this charge is displaced from A to the position B. Are you clear or not?
Yes, sir.
Now, if the charged particle is displaced from position A to the position B, then we can say there is a work has to be done. Am I right? Not?
Yes,
Okay.
sir.
Why? What is the reason? How can we say there is a work to be done? Because the equation of work done is W is equal to F.
To S,
And force is
force
if
into
force is
surface area.
applied upon a body and body gets displaced, then we can say the okay, there is a work done. Are you clear? So in this case, we can say here body is displaced from position A to the position B. So the body has done work. Okay. Now we are going to write here the work done by external force. Work done by external force in carrying charge Q from A to the B. Okay. We have W of external is
Yes,
equal
sir.
to integration of F of external dot dr. Okay. From position RA
Yes,
to
sir.
the position RB. Are you clear or not?
Yes,
This
sir.
is your W external. Okay.
Yes,
And
sir.
when you put value of W external from equation number 3, you can take it equation number 4. When you put value of F external from equation 3 into the equation 4, then you get here, put 3 in 4. We get W external is equal to integration of RA to the RB. F external is minus of Q into E, right? Dot dr.
Yes, sir.
Clear or not? Minus of Q E dot dr. You can
Yes,
take, okay, you can write it
EDR.
minus of Q into E dot dr, right? This is your work done by external force. Okay?
Yes, sir.
Yeah. Note it down, please.
Yes, sir.
Are you clearly understand till here?
Yes, sir.
Have you noted it?
So 1 minute.
Okay. What is your ongoing topic in your school, Harsh?
Sir, in school they are doing current electricity, sir.
Current
Third
electricity.
chapter. Sir, but like from next week I have my physics unit test, sir, on 22nd June.
22nd June, right? What is your syllabus for your next text?
Sir, the first two chapters, electric potential and capacitance, and the electric, the first one was electric field and charges.
Electric field and potential.
Charges and electric, yeah.
Okay. I mean, this topic is also in your syllabus of the test, right?
Yes, sir.
Okay, okay. Note it down,
Yes, sir.
please. Have you noted it?
Sir, 1 minute, 1 minute. I'm just work done.
Okay.
Done,
Can we
sir.
move on? Can we move on, Harsh? Harsh, can we move on? It's over or not?
Yes, sir. Yes.
Okay,
Yes,
good.
sir. Yes, sir.
This is your value of
Done, sir. Done.
W external, right? I'm going to write here again. Your W external is equal to integration of RA to the RB minus of QE dr, right? This is your equation. Okay. Now,
Yes, sir.
what will be the equation for uniform electric field? This is your equation for the non-uniform, right? Now,
Yes.
you can write here for uniform electric field. For uniform electric field, right? What is a uniform electric field? We can write again W external is equal to
External is equal
integration
to
of RA to the RB minus of QE dot dr, right?
QE by
QE dot
QE
dr,
DR.
dot
Yeah.
dr, right?
Yes, sir.
We can take minus of QE outside from your integration, and we can write integration of RA to the RB dr here, right? After integrating dr, you get
Yes, sir.
only and only R. Are you clear or not? From
Okay.
RA to
Yes,
the
sir.
RB, this is your integration of the dr, okay, in the bracket, which you get
Yes,
here.
sir.
This is your W external and W external, right?
Yes, sir.
Again, W external can be written as minus of QE R. R can be written as RB minus RA. Are you understand it or not?
Yes, sir.
RB minus RA. Now, this is your equation of the external work done in terms of position vector. Okay.
Yes,
So
sir.
this is your equation in terms of
Position.
position vector,
Position. Okay.
right?
Yes.
Where you can also write here RA and RB, RA and RB, right?
Yes, sir.
Are position vector of A and B, right?
Yes,
We
sir.
can also write W of external is equal to minus of QE, RB minus RA can be written as R of AB.
Yes.
Okay. This is the equation of work done by external force in terms
Sir.
of displacement.
Displacement.
Are you clear or not?
Yes, sir.
Yeah, because we have already know R of AB is equal to the RB minus RA.
Yes.
Okay,
Yes,
note
sir.
it down, please. I hope everything is clear or not.
Yes, sir.
Okay, everything is clear.
Yes, sir.
Note it down, please. I think you are study all of these topics second time, sir, right? First
Yes.
time in the school. In
Yeah.
school, everything is clear or not?
School, everything is clear.
Sorry,
Everything is clear, sir.
it was not cleared in the school.
No, it was clear. It was clear.
Okay, okay.
Done, sir.
Okay. Now, work done by electric field. This was the for uniform electric field, and now we are going to solve for work done by electric field. What is the work done by electric field? We have already from the last page, you can look at here. F external is equal to minus of F electric. Do you remember this equation or not?
Yes, sir.
So on the behalf of this equation, we can also write here W of EF is equal to minus of W of external. Are you clear?
Yes, sir.
Or you can also write work done by electric field is equal to what is your W external? We have W external is, this is your W external value, minus of QE RAB, right?
Yes, sir.
And place here QE, one second. We have already a negative sign here, and now W
Minus
external minus of QE
QE
R of AB, okay?
Yes, sir.
RAB. Now this negative sign will be positive QE R of AB. Okay?
Yes, sir.
This is your work done by electric field. Note it down.
Done, sir.
Good. Now we have a question. Note it down. We have a question. Find work done by external agent. External agent in the sense by external force, right?
Yes, sir.
In slowly shifting a charge Q is equal to 1 microcoulomb in electric field. Okay?
Yes, sir.
The value of electric field is given as E is equal to 10 raised to the power 3
Yes,
I
sir.
volt per meter
Yes, sir.
from point P 1, 2 to the point Q 3, 4. Note it down, please.
Yes, sir. Sir, I noted down the question.
Okay. Can you solve it?
Sir, I'll try, sir.
Let's see here. Your value of Q is given as 1 microcoulomb. Are you looking here?
Yes, sir.
Q is equal to 1 microcoulomb, which can be also written as 1 into 10 raised to the power minus of 6 coulomb. Okay.
Yes, sir.
The value of electric field is given as 10 raised to the power 3 I cap, and point P is 1, 2. 1, 2 in the sense 1 is in your I cap and 2 is for J cap.
J cap.
Similarly, for Q, it is your I cap and this is your J cap.
J cap.
Okay. So we can write here directly W external, I mean work done by external force,
External force.
from P to Q, right?
Yes,
We
sir.
can write minus of QE R of Q minus R of P. Okay?
Yes, sir.
RQ minus RP. Minus of Q. What is the Q? Value of Q. Value of Q
Sir,
10 raised to the minus of
1.1,
6.
yeah. Yeah.
Right? Into E. Value of E is
10
10 to
raised
the
to
power
3.
3 I cap. Okay?
Yes, sir.
And for RQ can be written as 3I plus 4J minus RP is your I plus 2J. I plus 2J.
2G.
When you open this bracket, we get 10 raised to the minus of 10 raised to the power 6 and 10 raised to the power, 10 raised to the power minus 6 and 10 raised to the power 3 will be 10 raised to the power minus of 3 I cap. In bracket, this is your 3I cap plus 4J cap minus of I cap minus of 2J cap. Okay?
Yes, sir.
Then we get minus of 10 to the power minus 3 I cap. After solving 3 I cap and minus I cap will be 2 I cap
2 cap.
plus 4J cap minus 2J cap will be 2J cap. Is it clear or not?
Yes, sir.
Now, look at here, please. This 10 raised to the power minus 3 I cap can be written as minus of 10 raised to the power minus 3 I cap plus 0 J cap. Is it right or not?
10 raised to 3 I cap.
You can write here 0
Yes,
J
sir.
cap or not?
Yes, sir.
And in bracket 2 I cap plus
2J cap.
2J cap. Finally, we get W of PQ external is equal to 10 to the power minus 3 I cap will multiply from 2 I cap. You get 2 into 10 raised to the power minus 3 plus when 0 will multiply with 2J, you get again 0 with negative sign here. Finally, we get W of PQ external is equal to minus of 2 into 10 raised to the power minus 3, right? Joule.
Yes, sir.
Okay. This is your final answer.
Yes, sir.
Note it down, please.
Done, sir.
Okay. One another question.
Yes, sir.
Calculate work done by external agent in carrying 2 millicoulomb charge from A 0, 0 to the B 2, 0 in electric field your electric field is x plus 2y I cap plus 2x j cap Newton per coulomb. Note it down, please.
Yes, sir. Sir, note it down.
Okay. Can you solve it?
Sir, I'll try, sir. 1 minute.
Okay, good.
Sir,
Yeah.
After we apply the formula, should we write 0 I cap plus 0 j cap?
Which part you are taking 0 JK?
Sir, it's the coordinates are given, right? A and B.
No, no. Look at here. Your value of charge is given here 2 millicoulomb, right? 2 millicoulomb will be 2 into
Yes, sir.
10
So
raised to
Coulomb
the
Coulomb. 2 into
minus
10 raised
3.
to 3 minus 3 Coulomb. Yes,
And
Coulomb.
now this is your I
Yes.
cap, and this one is your J cap. It
J
is your
cap.
I cap and it's your J cap, right? If you
J
want
cap.
to draw the diagram for this position A and B, then you can look at here. This is your I cap and this is your J cap. Okay. What
Yes,
is the position of A? A is your I 0, 0.
0, 0.
Comma 0
Yes,
is
0, 0.
at
And
origin. Are you understand?
origin, yes. Yes, sir.
And for B, it is 2, 0. 2 is
So it
along
is,
I cap and 0
I
is
cap.
along J cap. This means it is located here.
Yes,
Are you
sir.
understand?
Yes,
Are you
sir.
understand or not?
Yes,
Okay.
sir.
Right. Now, what is your
Yes, sir.
W external? W external will be
QE into RQ
RA
by R
to the
minus R.
RB minus of Q into E dot.
Yes.
Your value is given in terms of
QE.
X and Y. Okay, so we can write a QE dot dx, right? We are taking
Yes,
here
sir.
variable in terms of X, okay, not in S.
Okay.
Are you clear?
Yes, sir.
Now, your W external from A to B is equal to minus of integration RA to the RB.
Yes, sir.
RA to RB can be taken as, for A, it is your 0. I mean, your X is 0 as well as Y is also 0. And the upper limit, which is your RB, is only and only 2.
RB.
Okay?
Yes, sir.
Only and only 2 here.
Yes,
Because
sir.
another quantity is again 0. Your value of Q is 2 into 10 raised to the power minus of 3. Okay?
-3.
Yeah. Electric field.
Yes,
This
sir.
is your electric field.
Yes,
You
sir.
can write
X
here
plus 2y I cap plus 2x
X
j
plus
cap.
2y I cap plus 2x j cap
J cap.
dot dx.
Yes,
Okay?
sir.
Dot dx.
Dx.
Dx is also along I cap because it is your x axis. So we can write here dx I cap. Are you clear?
Yes, sir.
Again, integration of x is 0 from x is 0 and y is 0 to the point 2. It is your 1 second. You can take 2 into 10 raised to the power minus 3 outside from the integration. Minus of 2 into 10 raised to the power minus 3. This is x is equal to 0, y is equal to 0 to the 2. And now, when you multiply x plus 2y I cap from dxi, you get x plus 2y dx. Are you understand?
Yes, sir.
I cap and I cap will be 1. Okay?
Yes, sir.
Plus 2x j cap, and in this part there is no any j cap. So we can consider here your j cap is 0 j cap, right? And when you multiply 2x j cap,
Yes,
which
sir.
is 0 j cap, you get 0 again. Okay? So we can write here 0 j cap.
Sir, lagging, sir. Voice is.
Actually, I think from my side there is no any issue in network.
Yeah, sir. It's actually from my side, sir.
Okay, can you hear me clearly now?
Issues with my network.
Can you hear me clearly now? Hello.
Yes, sir. But when you are explaining, yes, sir, I can hear you.
Okay, once again I am going to explain here. Don't worry. When you multiply x plus 2i I cap with this part, you get x plus 2i dx. Are you clear?
Yes, sir.
And now there is 2x j cap and there is no any quantity in j cap. So you can take here j cap is 0. Okay. When you multiply 2x j cap with your 0 j cap, you get 0 again. Okay. You get 0 again. So we can write 2x plus 2i dx plus 0. Okay.
Yes, sir.
Now, W of AB external is equal to minus of 2 into 10 raised to the power minus 3. Your integral, I hope you have already know that you can integrate those functions which are already differentiated. Are you clear? So can you tell
Yes, sir.
me in this part, which one is differentiated and which one is not differentiated? You can look at here.
Differentiate it.
X is differentiated. Okay.
X is different. 2y is not differentiated.
Yeah, 2i is not differentiated. Okay. So 2i
Yes,
will be 0, and we are going to integrate only and only x now. X is equal to 0, y is equal to 0 to the 2 integration of x dx. Okay. Note it down, please. Then, okay, we'll continue. Note it down.
Done, sir.
Okay. Now, WAB external is equal to, after integrating, we get 2 into 10 raised to the power minus 3. After integrating, you get x square over 2. Right? From
Yes, sir.
0 to the 2. You can take 2 outside. Then minus of 2 into 10 raised to the power minus 3 over 2 in bracket x square. At the position of x square, first you put 2 square minus of 0 square. This 2 is cancelled with 2. You get minus of 10 raised to the power minus 3. This is your 4 minus 0. Finally, you get minus of 4 into 10 raised to the power minus 3. WAB external. This is your in joule. Okay. This is your final value.
Yes, sir.
Note it down, please.
Okay. Done, sir.
All right. Next topic is conservative electric field and potential. Conservative electric field and potential. Right?
Yes, sir.
Before study of conservative electric field, we are going to discuss about the conservative force first, right?
Yes, sir.
Conservative force. What is a conservative force?
Sir,
This is a type of force in which work done is independent on the path. Okay?
Yes, sir.
Yeah. Forces in which work done independent of path and depends only on initial and final position. Initial and final position. Okay.
Position. Yes, sir.
Are known as conservative force. Are known as conservative force, such as Some examples are gravitational, force, electric force, etc. Okay. You can understand here. Now we are taking a field. A charged particle is carried out from point A to the point B in 3 different paths.
Yes, sir.
Okay. The
Yes,
first
sir.
one is so this path. This is your path 1. We can say the work done is W1. When this charge is carried out from A to B from this path, your work done is W2. And when it is carried out from this path, this is your path
W3.
W3. Then we can write here W1, W2, and W3 all are okay.
Yes, sir.
From A to B. 1 second. A to B. This is your integral sign minus of QE dot dr. Okay. Note it down, please. Ash, I am coming in 1 minute. Okay.
Okay, sir.
Yeah. Have you noted it?
Yes. So 1 minute.
Okay.
Done, sir.
Write down here. Field corresponding to conservative forces. Field corresponding to conservative forces are conservative. Okay. Such as
Yes, sir.
electric field, gravitational field. Okay.
Yes, sir.
Electric field and gravitational field.
Gravity.
Right. Second point is total work done by conservative field in a closed path is 0. I mean, suppose that this is your field and a charged particle is carried out from A to from A to B first.
Yes, sir.
From A to B first, and then it carried out from B to A again. Now you can look at here, this path is closed. Are you clear or not?
Yes, sir.
this part is closed, and suppose this is your work done is W1 and this work done is of W2. So we
Yes,
can
sir.
write here W1 and W2 both are same, and finally we can say your minus of Q integration of E dot dr is 0. Can we say or not? Because
Yes,
this
sir.
is your W. You can write here W is equal to minus of Q integration of E dot dr.
Yes,
And your
sir.
W1 minus W2 are equal, or you can also write here W1 minus W2 is 0. Okay, so we can write
Yes, sir.
here minus of Q integration of E dot dr is equal to 0, or you can also write E dot dr is equal to 0. Are you understand or not?
Yes, sir.
Okay, and this is only and only for the closed path, and this circle on the integral sign represents closed path. Okay, you can also say this is your line integral of electric field. Okay, note it
Yes,
down,
sir.
please. Hence, we can say that the line integral of electric field is 0. Okay.
Yes, sir. Sir, it is land integral or closed surface integral, sir?
You can say it's closed path or line integral. Both are okay, useful here. Okay, both can be used.
Okay, okay, sir.
Yeah.
Okay. So done, sir.
Okay, and now if your line integral is 0, okay, you can
Yes,
note
sir.
here in the fourth point. If line integral of a field is 0, then that field can be represented as gradient of a scalar function known as potential, right?
Yes, sir.
Known as
Potential.
potential. Integration of E dot dr is 0. We have already know from above equation for a closed path, or you can say for the line integral. Then we can write here E is equal to d dr of V in negative terms. Okay, you can write it also. This is your scalar. Okay, electric. This is your scalar. Okay, electric.
Yes,
Right. Electric field is your vector quantity.
yes, sir.
Note it down, please.
Sir,
Yeah.
we won't be able to finish this chapter on Tuesday, right?
Sorry.
We won't be able to finish this chapter on Tuesday, right? Before Tuesday.
No, we can't finish this chapter before Tuesday
Okay, sir.
because it is a big topic.
Yeah, I know. Like,
Okay, it is not possible to finish. Okay.
then learn from
Yeah.
my school notebook.
Yeah.
Answer
Have you noted it?
Yes, sir.
Okay. Next one is your electric potential difference. Electric potential
difference.
difference. What is electric potential difference? It is a difference in potential at two different points. Okay. First of all, remember that electric potential basically defines electrical properties. Okay.
Yes, sir.
Are you clear or not?
Yes, sir.
A property which defines electrical. Electric potential defines electrical properties of a charge in scalar form, right? And
yes, sir.
electric potential is a property of single charge, not more than one charge, right?
Yes, sir.
So, right here,
V is equal to W by Q.
defines electrical properties of a charge in scalar form. Second point, it is a property of single charge. It is a property of single charge.
Charge.
Okay?
Yes, sir.
Yeah. Note it down.
Yes, sir. Done, sir.
Okay. Suppose that we are going to take a positive charge here, which can be also known as the source charge. You can say this is your source charge, right?
Yes,
If a
sir.
charge is placed at this position, then we have already know it creates its own field. Okay, and we are
Yes,
taking
sir.
different point in the field of this charge. Suppose this is your point A, and at this point A, the potential is VA, and another point is your B, and potential is VB. Are you clear?
Yes, sir.
Then what will happen? When you put a charged particle at point B, then what will happen? Suppose that we are only and only putting a charged particle at this point B. What will happen?
Only point. Charge particle point.
Yeah, at point B. Then we have already know this source charge apply a force upon the charge placed at B. Okay, in away direction. Why?
Yes,
because it is a positive charge.
Positive charge.
Yeah, and the charge placed at B is also positive in nature. Okay.
So repulsion.
But we are going to transport this charge from B to the A. Then if it is possible that this work is done by the field or this work has to be done by the external agent. How this work done is possible? This work done is possible by external force. Are you clear or not?
Yes, sir.
If the force is external, then work done also be external. And we can write here your change in potential. This delta V represent change in potential. Okay? Or yes, you can say potential difference. Delta V is equal to VA minus VB. Why we are taking VA minus VB? Because you can look at here, point A is closer to the source charge capital Q and point B is away from source charge capital Q. Okay? So we can say that potential at A is greater than potential at B. Are you clear? Potential at A is greater than potential at B. Are you clear or not?
Then potential at B.
Yeah. So we can write delta V is equal to VA minus VB, which is equal to the work done in transporting a charge from B to A externally. Okay. And that charge of magnitude Q. Are you okay?
Yes, sir.
This is your equation 1. What will
Yes.
happen if your charge is of 1 coulomb? Then we can write delta V is equal to VA minus VB is equal to W of VA external. Okay,
Yes, sir.
note it down, please. Have you noted it?
Yes, sir.
And now, can you tell me what is the value of W external? Can you tell me?
Value of W external.
Yeah, W external. What is the
Sir,
equation
so
of W external?
integral.
Yeah, W of BA external can be written as minus of integral RA
Yeah,
to the
RA plus RB minus
QE dot dr.
QA. Yes, sir.
Okay,
Yes,
you
sir.
can consider it equation number 2. Okay,
Yes.
now put this value, put equation 2 in equation 1. Then what you get? You get delta V is equal to VA minus VB is equal to WBA external is minus integration of RA to the RB QE dot dr over Q. Are you clear?
Yes, sir.
This Q is cancelled from this Q.
Yes.
Note it down, please. And when it is cancelled from this Q, then we can also write delta V is equal to VA minus VB is equal to minus of integration RA to the RB E dot dr. Are you clear?
Yes, sir.
Are you clear or not?
Yes, sir.
This is your also equation of electric potential. Electric potential difference. Okay.
Yes, sir.
This is your value of electric potential
Difference.
difference. 1 second, RB to RA. Sorry. Just there is a mistake. This is your RB to RA because we have taken a B to A. Okay.
Yes, sir.
RB to RA. RB to RA. RB to RA. Okay.
Yes, sir.
This is your equation form. This is your equation for non-uniform field. Okay.
Yes, sir.
You can write here for non-uniform field. Are you clear?
Yes, sir.
Have you noted it or not?
Yes, sir. Noted here.
Okay, good. And now can you tell me, suppose that your electric field is constant. Okay.
Yes, sir.
Your electric field is constant in this equation. Then what will happen here? We can write delta V is equal to VA minus VB, which is equal to minus of E integration of RB to the RA integration of dr. After integrating dr, you get delta V is equal to VA minus VB is equal to minus of E cap, minus of E vector. After integrating, you get R. Are you clear or not? R
Yes,
from
sir.
RA to RA. After expanding, you get R A minus R B. Are you okay?
Yes,
This is
sir.
a definition of electric potential difference in the form of position vector. Okay?
Yes.
In the form of
Position vector.
you can also write delta V is equal to VA minus VB, which is equal to minus of E. RAB. RAB can be written as R B minus A. RBA. Can we write it or not?
Yes, sir.
Your equation in terms of, or you can say in form of displacement vector, right?
Yes, sir.
Form of displacement vector. Note it down, please. And this is used, both of these equations can be used for
Potential.
uniform field. Okay?
Yes, sir.
When your electric field is
Uniform.
uniform. Note it down, please. Have you noted it?
So 1 minute. Done, sir.
Next point, electric potential.
Electric potential is defined as the work done bringing positive charge from infinity to a
Exactly.
point.
It is a work done in bringing
Bringing
a
unit positive
net
charge from
positive
infinity
test charge from infinity to a
to the
point
point.
against the electric field without acceleration, right?
Yes, sir.
Yeah.
V is equal to W by Q.
So you can write here, suppose that we have a field of positive charge Q, okay? And we have chosen a point A. We have chosen a point A and the potential at point A is VA. Are you clear?
Yes, sir.
And there is a point which is at infinity. At infinity, your potential at infinity is considered to be 0. We are carrying a unit positive test charge from infinity to this point A. Okay?
Yes, sir.
Carrying a unit positive test charge from infinity to this point A inside the field of this charge capital Q. Then
Yes, sir.
we can write here from equation of V A minus V infinity, which is equal to W of from infinity to the A external. Okay?
Yes, sir.
At infinity, your potential is 0. So we can write VA is equal to W infinity to A external over Q. What will happen if your Q is equal to 1 coulomb? Okay. If your Q is 1 coulomb, then we can write VA is equal to W infinity to A externally. Are you clear or not?
Yes, sir.
Okay. Now, in for variable field, you can say, just 1 second. This is your equation 1 and this is your equation number 2. Okay. Now, what is your W external to A? Sorry, W infinity to A externally. What is the value of this? This value can be written as from integration R from RB. RB is your infinity.
Infinity.
Infinity to RA. Okay. This is your position of RA. This is your RA. Are you understand it or not?
Yes, sir. Yes, sir.
RA and Q minus of QE dot dr. This is your equation number 3. Now put value of 3 in equation 2. You get
Yes, sir.
at A is equal to integration of infinity to RA minus of 1 second, just 1 second. Please.
Yes, sir. Yes, sir.
1 second, please. Yeah, integration of infinity to RA Q into E. Everything was correct, okay, but just for arrange this equation, okay. QE dot dr over Q. Q is cancelled with Q. Finally, you get VA is equal to minus of infinity, minus of integration from infinite to RA E dot dr. Have you noted it or not? Sorry, are you understanding or not?
Yes, sir.
Is there an issue?
No, sir. No, sir.
This is your scalar quantity and the SI unit is joule per coulomb, or sometime it is also known as volt. Note it down, then we will write the definition of electric potential, okay? Because
Okay.
we have already calculated the equations of electric potential, but not okay, till now we have written the definition. Okay, note it
Yes.
down.
Done, sir.
All right. Now, please note down the definition.
Yes, sir.
Definition is electric potential at a point is the work done by external force in carrying a unit positive test charge from infinity to that point against the electric field without acceleration. Okay.
Yes, sir.
So note down, please. Accelerated charge will generate electromagnetic wave. Okay.
Yes, sir.
Yeah, note it down, please.
Done, sir.
And now this is electric potential is over. Okay, electric
Yes, sir.
potential difference and electric potential both is over now. And now can you solve a question right now? Please note down a question here.
Yes, sir.
Electric field in a region is E is equal to A over X cube I cap calculate potential in this region. Can you solve it?
Sir, 1 minute, I'll try, sir.
Sorry.
I'll try, sir. 1 minute.
Okay.
Sir, so it will be integral of A by X cube I cap into dr, right?
Exactly. E dot dr, you can use it. V is equal to E dot dr, right?
Yes, sir. Sir, but after putting it in the formula,
You can use it. V is equal to integration E dot
E
dr.
dot dr, yes. So for E, we'll put the value A
This
by
is
X cube.
from infinity to X. You can take it.
Yes, sir.
And now your value is given in terms of X. Okay, so you can put it here, not sorry, at the position of dr, you can put here dx.
Dx, okay.
Because your value is given in the terms of x here.
X.
Okay. Are you understand or not?
Yes, sir. Yes.
So this is your negative sign here.
Yes.
Integration. And what is the value of e?
E is a by x cube I cap.
X cube I cap, right?
Yes, sir.
Dot dx. X is your I cap. Again,
Yes, sir.
I cap from infinity to x. Then minus of a can be taken outside.
Yes, it can be.
A can be taken outside from integral.
Yes, sir.
Integration of a infinity to x. A, sorry. 1 over x
1 by x cube I cap.
1 over x cube dx.
Yeah.
Right?
Yes.
Or you can also write minus of a integration of infinity to x to the power minus 3 dx. Are you understand?
Yes, sir. Because
Then
it came up, so to
all of this is your v. Okay.
Yes, sir.
V is equal to minus of a. After integrating x to the power minus 3, you get
3
x to the power minus 3 plus 1
plus 1 over
minus 3 plus
3 plus 1.
Okay. From
Yes.
infinity to x minus of a x to the power minus 2 over minus 2 infinity to x. This minus 2 and minus a. Okay.
Yeah.
You can look, it will be positive. Right.
Yes, sir.
So it is your a over 2. You can write here minus a minus 2 and x to the power minus 2 infinity to x. This minus is cancelled with minus. Again,
Okay.
you get a over 2 and we can write 1 over x square as 1 over, sorry, x to the power minus 2. We can write 1 over x square. Okay.
Yes, sir.
Infinity to x. V is equal to a over 2. At the position of x, first you put here x square minus 1 over infinite. Okay.
Yes, sir.
Again, you get v is equal to a over 2x square volt.
Okay.
Right. This is the final answer.
Okay. Done, sir.
Okay.
Yes, sir.
And now, today we are going to over this class now.
Okay, sir.
And we will continue from this point in the next class. Everything is clear or not?
Yes, sir. It is clear.
Tell me honestly, please. Everything is clear. Is there any issue?
No, sir. It's no issue.
Okay. All right. Okay. Thank you.
Thanks, sir.